TST versus BST. So in this scenario, we're considering a string of length 3, and we're considering 10 strings insertion worst case for TST and BST. And we want to determine the height for both of them. So for TST, each node stores a character. So if the first string, it will be 3 characters long, so 3 nodes, 1, 2, 3. And then for the next string, let's just say it has the same characters for the first two, but then the next one is like less than here. And what if all of them is less than? So this is the second string, this is the first string, and this would be the third string, fourth string, fifth string, seventh string, sixth string, seventh string, eighth string, ninth string, and 10th string. To determine the height, we want to count the links. So here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the height for the TST is 11. Next, for the binary search tree, each node stores the string, not a letter. So here it will be 1, this is the first one. And then let's say all the rest of the strings are less than it. So we'll go here, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total, count the links up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the height of the binary search tree is 9. The next part of the assessment is corresponding trees. This is here we have the binary tree. As you can see here, the double links represent a red link. So question 1 asks, what's the height of the tree? So what I did was I looked at the double link and I ignored this. I didn't consider this as a height because it's combined technically. So I would go here 1, 2, and for the right side it'd be 1, and here it's combined, so 2. So the height is 2. Oh, sorry, I meant to say that this was a 2 to 3 3. Next, for question 2, it's asking for this corresponding 2 to 3 3, what is the least amount of nodes I can add to this tree so that there's a height increase? So for this question, I approached it like this. So I knew that the equation for a tree, for the minimum amount of nodes in a level, is 2k minus 1. So k is the level. So this is the minimum number of nodes per level, where k is the level. So right now, the level of this tree is height plus 1, and since we figured out that the height was 2, that means the level for this tree is 3. But then we want to cause a height increase. So when a height increase, the level is the level will increase by 1 since the height increases by 1. So the level we want to look for is 4. So if k is equals to 4. So if we put that in our equation, 2 to the power 4 minus 1 is 15. And now we can just count with how many nodes there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So 15 minus 12 is 3. So the least amount is 3. Next, for question 3, it asks, what is the most number of nodes it can add to the corresponding 2 to 3 3 until it changes the height or increases the height by 1? So as we discussed before, the level for this tree is 3. The level is 3. So we want to look at the maximum number of nodes a 3-level tree can hold. The formula for it is 3k minus 1. So if I put 3 in k equals to 3, 3 to the 3 minus 1 is 26. And just now we counted that the number of nodes in this tree is 12, so 26 minus 12 is 14. And 14 is the answer we're looking for. For question 4, the question asks how many number of nodes or the least number of nodes we can add to the corresponding LLRB tree. So now it's an LLRB tree, not a 2 to 3 3, to increase the height. Well, to increase the height, we have to try and input a node where it wouldn't break the invariable of the 2 to 3 tree. So if I add one node right here, let me look at it. So the red link is at the left side of this node. Does that break the rule? It doesn't. If it's at the right side, it would, and it would cause a rotation. But if it's at the left side, it wouldn't, and the height did increase, as you can see. Now that it's 4, or wait, 1, 2, 3, 4. Yep, the height did increase, so it's now 4 instead of 3. Lastly, for question 5, it asks, what happens if you add the largest value to the corresponding LLRB tree? So if we added to the LLRB a really large value that's bigger than all the values on the nodes, it would go, is it greater than this? Yeah, so it would go right. Is it greater than this? Yep, so it would go here. And it's also larger than this, so it would go to the right side. So I'll add a node right here. However, if you look at this, I should also say that the reason why it's a red edge one or a red link is because that in the code for an LLRB, every new node you add will always be a red link. And okay, now back to it. Now that we've already added it, let's see if it breaks the invariant. Oh, it does break the invariant. So at the right side here, you can see that the pair node can't actually have a right red link. It can have a left one, but it can't have a right one. So what this will call, it'll call rotate left on the parent tree, which will break this and make it go here, which fixes the invariant. Well, I mean, the parent will be here, and this one will go on top. Thank you.